Okay, thank you. I am Bineet from India. I have just completed my PhD from the Indian Institute of Technology, Roorkee. And here I'm going to present a part of my research, that is characterization of the fracture behavior of UHPFRC by considering the influence of the specimen size and the fiber content. So if you talk about the UHP of RC, basically the fiber reinforced concrete. So why it is using, because it is in a demand due to its high compressive strength, having high flexural strength. It is very good having ductile nature. It can be used for a slender structure construction. It has excellent durability, and now it is being used for a repair and maintenance work, and it is having lesser maintenance cost. Though its cost is high, but for maintenance and repair work, it is very good. So these are the positive point for USP of RC, but still there are so many of questions which we are looking for. Even people are doing research to find out those answers, and they are trying to, means if we can produce a good constitutive model. So considering all the factors, like earlier you have seen the unique post technique behavior because it is having very ductile nature. What would be the effect of fiber content and how we can manage? What would be the effect of a specimen size? And if we talk about the fiber, then wall effect will also come because of fiber orientation, fiber type. We are using hooked end, straight, crimped. And what would be the stress profile, like stress strain or stress crack opening? And what kind of fracture mechanisms involved in its post technique behavior? So there are so many questions as people are looking for it, and even research are going on. So if we can conclude all the questions, and if we will try to figure it out by considering all the parameters, and if we can produce any constitutive model, so it will be a great help for the designers. So in our research also, we have tried to address all the questions. Like they have conducted the experiments for varying specimen sizes. Here we have performed basically the flexural load test by considering geometrically similar beam specimen, and we have also considered two different fiber percentage, that is 1.5 and 2.5. Again, it is fiber percentage by volume. So this is our experimental setup. This is a flexural load setup. You are able to see it, where we have used the LVDT to monitor the crack mouth opening, or you can say the crack opening. We have also used the digital image correlation technique to figure out the surface damage. And this is how the flexural loading has been conducted for the geometrically similar beam specimens and for both the fiber percentage. This is the experimental result. Basically, here I'm showing the load CMOD relation, and it was under CMOD control. So these are the two test results you are saying. It is interesting to observe in case of 1.5% fiber, after peak loads, there is a sudden drop down, and after that it is increasing, and again it is going in a softening mode. But it is not in case of 2.5% fiber content. It is showing the smooth behavior. So why these things are happening? Because it is the effect of fiber percentage. Later we will discuss. And second one, what I had talked about, that what would be the effect of a specimen size. As you will clearly see, for a larger specimen size, a drop down rate in case of softening is more for larger specimen sizes. However, in case of smaller specimen sizes, it is bit showing some plastic nature. So these are the effect is coming from the specimen size and fiber percentage. Later I will also talk about the fiber orientation. So till now we have observed the experimental results, but to formulate or to give a constitutive model, we need to have an analytical formulation. So we have formulated an analytical model. Here I'm not showing all the mathematical formulations, just I will give you the outline. So basically what we have done, we have proposed a stress profile for compressive as well as for tensile, and we have considered all the factors like specimen size, fiber orientation, wall effect, whatever it was, but I had discussed earlier, and we have performed the inverse analysis approach. Whatever the load CMOD behavior we have obtained from the model, that has been calibrated with the experimental result, with what we are getting. And later on, whatever the model parameter that have been derived, that has been used to calculate the crack propagation with the crack opening. And later on, it has been validated with the DIC results. So this is how the work has been carried out. The stress profile, what we have selected, the tensile and compressive. The compressive, we have selected the elastoplastic because since last 30 to 40 years, we have seen people have considered this profile suitable for UHPFRC or FRC samples. But in case of tensile, it is interesting because it is not a plain concrete, it is having very ductile nature. So we cannot simply consider the stress strain approach. But initially there is no crack opening, so we are bound to consider the stress strain approach. So what we did, we just combined both stress strain and stress crack opening. So till we have decided one point, actually that is the strain limit. We have decided one point and bifurcated. Up to that point, there is a stress strain approach we can apply, and after that, that is the stress crack opening. So let me explain you how I have taken this profile. So initially, what will happen? It is in an elastic state, and after that, the first crack will occur. Basically, initially, it will show some kind of plain concrete nature, because unless there is no crack opening, fiber will not comes into picture in case of bridging. I'm talking about the bridging. So this is the plain concrete nature. So it gets cracked. And yeah, one more thing I forgot to tell you, that UHPFRC has been developed by considering mortar. Aggregate has not been used. So this is why it is showing very brittle nature initially. When fiber will come, it will present in a ductile. But yes, after the first crack, the stress carrying capacity has decreases. And when fiber comes into picture, it will try to bridge that gap, and basically it will try to reduce the crack propagation. Still, we can apply the stress strain approach because there is no clear crack opening. And up to the fiber bridging point, means the end of bridging point, means after that the fiber pull out will take place, means the clear crack has occurred. Of course, it is not a traction free. There are fiber to bridge, and they are trying to resist the crack propagation. But what will happen if we talk about the fiber orientation, the third figure? Here you will see I have shown the hooked end fiber, and I have taken the phi as a orientation angle. So what would be the effective length that is actually contributing in the bridging? That is L cos phi, not the total length of fiber. So we have considered the average effective length that is actually contributing, that is L cos phi. So what will happen when fiber will try to get pulled out? There will be yielding, because fiber is hooked. There is at two different points there will be yielding, and at the simultaneously it will be yield and it will get pulled out. So while pulled out, there will be some loss of frictional resistance, and once that both the yielding has been completed, again there will be one yielding. So this is how the stress carrying capacity has decreases, and again there is a loss of frictional resistance. So this is how the fiber orientation and the stress strain approach and stress crack opening approach all have been considered in a model, and inverse analysis has been carried out. So these are the calibration result, what we have obtained from the model. It has been calibrated with the experimental result, and you will see this has been done for the small specimen size for 1.5% fiber content, and you will see it is perfectly going with the experimental result, and it is in line. And whatever the result we have obtained from the DIC, it has been validated with the model result. Like model result is in line with the DIC result. So we can say the model is predicting a good results. Isn't it? It is in line. Later on, whatever the model parameter that has been derived from the calibration studies, you will see the material parameter, basically it is constant, means it is not changing much if we are differing with the specimen sizes. Like material parameters are constant, but the strain limit or crack opening limit, that is changing, means it is increasing when we are decreasing the specimen sizes. And why this is happening? It is established that relative fracture process zone length in case of smaller specimen sizes will be less higher compared to larger one. So the model is also aligned with the similar case. Because here also we have found that the strain limit or the crack opening limit is higher for smaller specimen sizes. At the same time, if I talk about the 2.5% fiber content, the material property is slightly improved compared to a smaller fiber content, and which is very obvious because bridging property will improve. So these are the model parameter we have been derived. And one more thing, the fiber orientation factor. Fiber orientation factor means the angle phi will be more for smaller specimen sizes, because the wall effect comes into picture, and because of that wall effect, fiber, if specimen size will be lesser, the fiber will try to align. So we have also considered the fiber orientation, and you can see the results. These are the stress strain behavior which has been derived from the model, and for both the fiber content, you will see for smaller specimen sizes, the strain up to which the strain criteria can be applied, it was around 0.8%. However, for larger specimen sizes, it is around 0.4%. and it is nearly same for 2.5% fiber content also. So it shows that the fracture mechanism behavior means the relative fracture process zone length will be more in smaller specimen sizes. It was the stress crack width behavior for both the fiber content, and it clearly shows that up to what percent or what crack opening we have applied the stress strain approach and crack opening approach for both the fiber content. And the same thing what we have seen earlier, the strain limit will be higher for strain limit, or you can say the crack opening limit will be higher for smaller specimen sizes. This is the crack propagation behavior for both the fiber content. Of course, more or less for all the sizes, it is showing similar trend. But interesting thing we can observe, nearly at 0.5 mm crack opening, basically the crack length has occurred. And after that crack opening, 0.5 crack opening, there is no increase in crack length, rather crack opening will increase. And it is obvious when we talk about the fiber content, mostly damage occurs because of plain concrete. And once damage has occurred, only the fiber bridging will take place. This is why crack opening has increasing, but crack length is not increasing. And this is the comparison of fiber content. So how the stress strain profile has changed if we are using the different fiber percentage. Like in case of 1.5% fiber, you are seeing there's a more stress drop down, and again it is increasing. But in case of 2.5% fiber, there is no that much drop down. The reason is when crack is propagating in its path, if it encounter lesser number of fiber content, then obviously there will be less bridging and the stress carrying capacity will decrease. But in case of 2.5% fiber content, there will be more fiber, though. So the strain limit will not go much. Like the stress carrying capacity will not decrease much, and later on it will show the fiber bridging, and it is the frictional loss. And similarly, the bridging behavior of 2.5% fiber content is more superior for 1.5% fiber content. So the crack, for any crack opening, there will be lesser crack length reported by the sample which is having 2.5% fiber content, which is obvious. So this study represent what we have seen. We have included both the stress strain approach and stress crack opening approach to formulate our model, and that can be used for a design purpose. We have considered the fiber orientation, specimen size, how it will influence, and how we can model it. What kind of fracture mechanism involved in its post cracking behavior. Of course, one more thing, that fiber distribution should also account, because it is again the matter of investigation and we are looking for it. So this is how it was, my research, and thank you for your kind attention. That's it.